Okay, so today we will discuss the possible version of mean value theorem and application. There are many applications, we will discuss one application. So, I will mention about it in my lecture of course. You see, let us recall what the mean value theorem for function of one variable says. So, suppose I have f from an interval a b to r and f is differentiable on a b, entire a b, right. Now, if I take any 2 point x 1 and x 2 in a b, then the mean value theorem says that the difference f x 2 minus f x 1, this is given by, so value difference between these two is given by f prime xi into x 2 minus x 1 for some xi between x 1 and x 2. Some xi here. It just says what is important here, you can write it in this form, but this theorem does not give what is xi, it just give that this will be given by f prime xi, or in the other way to say that f x 2 minus f x 1 divided by x 2 minus x 1, right, f x 1 f x 2. So, this is the difference between f x 1 and f x 2. So, this ratio is tan of this angle, tan theta. So, this ratio, the date which is tan theta of this angle, that is given by, so if I divide by this thing, that is given by gradient at some point. Actually, it is a direct application of Rolle's theorem, the proof. Now, to generalize it for a function from say u in Rn to Rm, first thing we encounter that I must, and suppose x and y are 2 points in u, here is your u, x and y 2 points. Now, to make sense of xi, you see it is in between x 1 and x 2 in the interval. To make sense of a in between point and x and y, we need some notion of that. So, what is in between 2 points in an open set in Rn? Well, so most natural is that you join x and y and you get a line over here. If the line entirely belongs to u, it is p naught. I will see example, and xi is some point here, z or z is some point here. So, in between points of x 1 and x 2 are points of the form sum all the points in the line, that is some T x plus 1 minus T y T in 0 1. You see, if you start at 0, you are at x, you are at y, and start and end up at 1, it's you are at x, and in between points, all these points can be expressed by T x plus 1 minus T y for some T in 0 1. Okay. So, we should expect that a statement like this hold. that MBT should read like Fy minus Fx equal to df at some z y minus x, where z is for some t naught in 0 to 1. That will be the exact analog of this statement. This is what should you expect for MBT in several variables. Unfortunately, this does not happen. This is not true. Why? Let me show an example. Okay. I take f from the entire R to R2 and I take a very simple function cos t sin t, t in R. If such a statement is true, if what we expect is true, then what it should be? Should have given T1, T2 in R, there exists T naught in between T1 and T2 such that f T2 minus f T1 equal to f prime at T naught. F is from R to R2, so this is a 2 cross 1 vector, right, or should I write df according to our notation, df at T naught acting at T1 minus T2, oh sorry T2 minus T1. Okay, this should be true. Let us check. Let us take T1 equal to 0, T2 equal to pi. What is f T2? Cos pi 1, sin pi 0. What is f T1? Cos 0 1, sin 0 0. So, left hand side is 0 equal to 0 is 0 0 of R2. What is df at T naught? This is very easy, minus sin T naught cos T naught, right, and T2 minus T1 is, so is 2 pi minus 0, oh sorry not pi, 2 pi, cos 2 pi is 1 and 2 pi minus 0 is 2 pi. So, this will be equal to 2 pi into this vector cos T naught sin T naught, where T naught is in between 0 to 2 pi, some number, that is if I follow this. Now, then there is an immediate problem. What? Let us take norm on both sides. This is the norm of 0 vector, which is 0, and here is 2 pi into norm of this vector is cos square T naught plus sin square T naught 1 root over, that is 1. So, I will get this. So, which is a straightforward contradiction. So, this statement does not hold. So, to make it hold, what we need, that MBT actually depends how do you look at the function, and when you look at a function, the graph of a function, or in R3 the region of the function where it is defined, you look it from a direction. and once you fix a direction, that is going to be true. So, what I mean here is the statement of MBT in for functions of several variable, you have to fix a direction. So, here goes the statement of MBT for function of several variable. So, f is function from u in Rn to Rm, f is differentiable on the entire u, and let x and y be two points in u such that the line joining x and y, that is T x plus 1 minus T y, belongs to u for all t in 0 to 1. Okay. So, situation like this, so u may be an element like this or maybe a open connected set like this. I have x here and y here, not here, but line joining x and y. So, I should have x and y like this or x and y like this. I cannot take x and y like this, because this line joining x and y is not in u. So, I have to take x and y such a way that the entire line joining x and y is in u. So, fix any u in Rm. You can choose arbitrary Rm. So, this is a kind of fixing a direction, fix any u, but once you fix it, fix for the statement of the theorem, but okay. Fix any u in Rm, then there exists a T naught. So, something in between the line joining x and y, so that if I take z equal to T naught x plus 1 minus T naught y, then f y minus f x equal to, okay, I have to fix, look at its direction. Okay, let me write it later. What is the direction means? F z at y acting at y minus x, which is not true. So, you have to look at from the direction of u, left hand side and right hand side. This is the correct statement for MBT for function of several variable, and the proof is extremely easy. How? So, x and y is in u, and we have always taken u, remember from the beginning of this course, u open connected. Many statements are true, whatever we have proved just for open, but here I emphasize I need connectedness. So, maybe for that in the statement I include this part, that here u is open, very good, open I need for differentiability, and connected emphasized. So, I need u connected. Okay. So, the proof is here. So, choose a delta greater than 0 such that T x plus 1 minus T y belongs to, so this line is a subset of u, but this is already my assumption, but here I have chosen this line little bit extended. This is because I want to apply differentiability and I do not want to apply differentiability at end point, but I can do this. Why? Because you have chosen open. So, if x is there, there is a ball around this. So, I can always extend this line little bit inside u, and here also there is a ball around y. So, I can always extend this line little bit beyond y. So, I choose t between 1 and minus delta to 1 minus delta, and I will apply for the point 0 and 1 in between. So, consider the function f t equal to u dot f of x plus t h, where h equal to y minus x. What is f prime at t? F is differentiable by chain rule. This is f df at x plus th at h. This is chain rule. Okay. Apply MVT for one variable. F is from minus delta to 1 plus delta, this interval to R. MVT for one variable function will imply there exists a T naught, MVT one variable function with 0 and 1 in minus delta to 1 plus delta. So, there exists a T naught in 0 to 1 such that f of 1 minus f of 0 equal to u dot d x plus t naught h at h is y minus x. What is f 1 minus f 0? F 1 is y, f 0 is f x. D, call this z naught, z at y minus x. So, your z is x plus t naught h, and if you write y equal to y minus x, you get z is in this form, maybe 1 minus t naught and t naught, but that does not matter. So, this is a proof. Let us look at it carefully, you will work it out. So, this is the proof of MBT. And now, as for the application, which is very fundamental, and you all of you use it, and all of us use it randomly. Whenever we see a function, differentiable function which is 0, derivative 0, we say f is constant. So, that is what we want to prove now. So, as an application, I have this theorem. So, again f from u to r, u in Rm to Rm. Let me emphasize, u is open, connected, f is differentiable on u, and for all x in u, dfx is equal to 0. So, as a linear operator, this is 0. dfx is a linear operator from m Rn to Rm. So, as a matrix, m cross n is 0. Then f is constant. There is a constant in, it is a fixed vector in Rm, and this is a direct application of MBT. How? Proof. See, just think about it. I will not write the entire proof. Suppose U is this kind of set, that whenever x and y in U, so whenever x and y in U, the line joining one x and y is also in U for all t. That means such a set is called convex set, right? Any 2 points is there and the line joining is there, is always there. Now, you can apply MBT directly. How? MBT will say to tell you f y minus f x, you fix any direction u, correct. So, fix any u in R m, this is going to be equal to u dot d f z y minus x. So, z is of the form some t naught x plus 1 minus t naught y, just what we prove it, correct. But this fellow is 0 matrix operator. So, this side is inner 0, inner product with u, which is still 0. So, u dot f y at z is 0 whenever I fix u. Now, you can take u to be f y minus f x, x and y are fixed. So, f y minus f x dot f y minus f x will give you norm of f y minus f x norm square equal to 0, norm square of something equal to 0 will imply f y minus f x equal to 0. So, f and f y equal to f x, and you can apply for any 2 points as long as u is convex, any convex set is open connected. But one may immediately recognize there is a problem. What is the problem? U may be open and connected, but it may not be true that for any x y they can be joined by a line. For instance, if I have my u like this, and here is my y, here is my x. If you try to join it by a line, this part of the line will go outside u, or for that matter u is like this. Here is my x, here is my y. I cannot join x and y by a line, it will go outside. But what I can do always, you see, I can still do a simple trick. I do not join x and y directly, I put a point in between z, join x and z and join x and y. Here also I can choose not one z, but maybe many, and z1, then a z2, then a z3, then a z4, and then finally y. So, I can join them by broken lines, polygonal lines. So, I can join x and y by polygonal lines, meaning choose z naught may be equal to x, z1, z2, zk, finally which is y, all zi in u, such that zi plus 1 to zi, this line lies in u. Now, you do what? You do simple thing, you apply MBT on the each broken part. So, f y minus f x, first I apply MBT to f z minus f x, here I will get f z1 equal to f x, then I will apply to z1 z2, here I will get f z2 equal to f z1, so on, and finally f y equal to f z4, f z3, f z2, f z1, f x. So, f y equal to f x. So, write down the proof now. But here remains a catch. What is that? That given any open connected set, I will be able to do it. This is a very nice exercise, I will put it in the assignment, but let me just for 1 minute give you the hint how to prove it. So, this proof is okay, modulo I prove this statement, any u in R n which is open connected, then u is polygonally connected. That means precisely this, that is given x and y in U, there exist point z naught, z1, zk for some k, all in U, zk equal to y, all in U, such that these lines zi plus 1 zi, this line entirely belongs to U, I equal to 0 to k minus 1. If I prove this, this proof will work fine. And here I use connectedness, and for that what we do? I put it in assignment, so you do it all yourself. You put a subset A of U, so fix any point x naught in U. Consider all point y in U such that y and x naught can be joined by polygonal lines, that is these broken lines. A is a non-empty set and you show A is open, and you take B equal to A complement and you show B is also open. So, you can write U as A union B, two disjoint set, and both are open, U is connected. It is very easy to then it is obviously it will follow that U is either A or B, one of them has empty, but A is non-empty. So, B is empty. So, A is entire U. So, do this exercise, it is in the assignment 2. Okay, that will end.